morning, everyone. All right, I will get the participant window and the chat window, and I will start today's lecture. Maybe I can show you the code as well. So let me open this one too. Yeah, it was here. All right, so we're all set up. Let me put it down. All right. Okay, so hello again, everyone. Today I'm going to finish the ray tracing shading part, and if we have time, we're going to start talking about texture mapping. By the way, your assignment is posted on Friday, and as you can see, it's you will basically be implementing what we have talked about in class. Some utility code is provided for you to write ppm files and read the scene. The scene will be different from what we have in the simple ray tracing that I showed you. It's a more structured format, uses XML format to describe the camera and the scene and the objects and the materials of the objects. So everything is really structured, and a reader, an XML reader which is using the tiny XML library, I think, is provided also along with the assignment. So all those input-output stuff you will not need to do yourself. You will basically be implementing the ray tracing algorithm that we have seen in this class. All right, so before I start, do you have any questions about the assignment or the ray tracing up to this point in general? Any questions? Anyone? All right, so I hope that everything is going smoothly, and the material that we're covering, you can follow. You can follow up them easily. So I hope the material is not that difficult, and it will be a nice experience. I mean, after you, as I said, if you write this algorithm, seeing the output is really rewarding. I mean, writing some simple mathematical equation and seeing the effect on the final image, it's really nice, especially when you add the reflections. Your scene is going to look much better. Shadows, you just write a very simple shadow function, and immediately with the addition of shadows, your scene looks really nice. So these things make the ray tracing algorithm, and this course in particular, very nice. I mean, this may be the first times you see some non-textual output in something that you code. I mean, of course, there are some graphical user interfaces you may have developed before, but this is really nice to have a picture, a photograph of some virtual world is something really interesting. Okay, so let's continue with the shading models. Last time, I quickly went over the basic illumination model. So this basic illumination model is composed of 3 different components, and it's just about the interaction of the light with respect to the viewer's position, the object's position, object's point at that this normal of the surface at that point, and things like that. So it's a simple model, as the name implies, this basic illumination model, and it's composed of these 3 components. The ambient shading part is like the global default light that is available everywhere at every point. And we also talked about the material properties. What we have is every object in our scene has reflectance coefficients, which I denoted as K, which determines its color basically. So when we compute the color of a ray, we multiply the light's intensity with the reflectance coefficient. And this multiplication is not like dot product or cross product. It's actually we're multiplying two vectors and we multiply each component individually, and the result is another three-dimensional vector, which is the RGB color. So this is how we basically implement the interaction of light with the objects. And also one thing that can be really interesting is that this is what OpenGL allows you to do. When we come to OpenGL, a computer graphics library, you're going to see we'll have these parameters in OpenGL as well. We will have an object may have different sets of reflectance coefficients for all these three components. I mean, it doesn't make sense. I mean, if an object is green, for example, it should be, its material should be green, right? It cannot have, for example, what we will have some really unnatural flexibility, which will saying that, okay, this is an object which can shine specular light in yellow color, but its diffuse color is in red light. I mean, in other words, its diffuse color is, its reflectance coefficient is red. It's like red material, but its specular reflection is yellow, and it interacts with the ambient. It's also, its ambient reflectance coefficients are blue. They can have, so in other words, we will have these components. We may have different reflectance coefficients, KD, KS, KA, for the same object. This is not natural. I mean, basically in reality, objects cannot show this different behavior on diffuse or ambient. They should have the same material, but this is some flexibility OpenGL and gives us, and we can, since we are the ones who are coding it, we may have these different material reflectance coefficients for an object. I'm not sure in the homework assignment, is it like this when the objects, I can actually open up, let me look at the assignment document as well. So here, let me just log in out to class. All right. So this is my account. So here is the assignment. Somewhere here. Yeah. This is the PDF. All right. So if we take a look at the format. Oh, by the way, as you may have, if you have read the assignment document, you may have seen you're going to implement light attenuation, in which the distance of the object to the light source will be considered in determining the intensity at that point, and the intensity will be reduced in inversely proportional to the square of the distance. Okay, so you will be just implementing this simple function, and this H, you should use Blin-Phong shading, means that in order to compute the specular component, you're going to use the half vector idea that I'm going to repeat that again. Okay, so if we look at the material properties, yeah, you see, yeah, it's actually Alparslan answered this question. A material can be defined with ambient, diffuse, specular, and mirror reflectance properties for each color change. So for the ambient, you will be given different reflectance coefficients for the same material. For diffuse, different reflectance coefficients. Specular, different reflectance coefficients. So it will be really interesting. I mean, you may have a red sphere, but the shiny spot could be yellow. Okay, so this will allow you this flexibility. All right. So yeah, and it's basically describing what we have covered in the class. But if you have any questions, let me know. Also on Thursday, in our Thursday lecture, if you have any questions about the assignment, I will be happy to answer them during class hours. Yeah, and I suggest you start the assignment as soon as possible. Don't leave it to the last 3-4 days because it takes time. And the good thing about this assignment is it's incremental. You can first get your first intersection test, the geometry part, and see whether you see the objects in their correct positions. You are able to generate any kind of image with the same color all over. You may try to generate, for example, black and white image first, then consider material properties into account and implement the basic illumination model next, the diffuse lighting, ambient lighting, and then add specular to that. So everything is incremental, and at each of those increments, you're going to see your image evolving to the final version. In which contains shadows and reflections as well. All right, so but I suggest you start as soon as possible. Do not leave the assignment to the last 3-4 days. All right, so let's continue with our model. So as I said, materials may have multiple reflectance coefficients, which may not be natural, but what we have is in our shading model, which is composed of ambient, diffuse, and specular. In diffuse shading, which is one thing, in some key points in diffuse shading is that the only things that are important in diffuse shading of that surface point X is its normal vector. So this normal vector and light's position. We have two vectors that we take into account. This W0, which is the vector to the camera, is not taken into account, meaning that whatever color we have, we compute for this spot X, we will not be the cat is all over the place. So the same color will be seen from any position around the scene. So the camera position is not important in diffuse shading. So we compute the color at the diffuse component. The computed color only is based on the normal vector along the surface point at that point, and this normal vector we compute for this, whether it's a triangle or a sphere, we may compute very different normals. One thing that is really interesting is that you're also free to compute this normal in any way you want in general, not in the assignment, of course. In the assignment for triangles, you will have the same normal vector for a triangle surface along its surface. For a sphere, you're going to compute the normal from the sphere center to that point. So you will use a certain technique. But what I mean is that by playing with this normal, we can have introduced different effects. And I mentioned some of them in the previous lectures, like bump mapping. By playing with this normal with some noise, I can have a pattern on the smooth surface of a sphere, which will make it look like an orange's surface, non-smooth. Or we can have a sphere represented by triangles, in which case if you have same normals for triangles all over the place, you will see it as if you will see the boundaries of the triangles, because for every triangle you will basically, the diffuse component is going to be constant along the triangle surface because its normal is the same. Maybe this vector is a little bit changing. It's not going to be same, but it's going to be basically, you will be seeing the boundaries of the triangles if you use lots of triangles to represent a sphere. Okay, but what I'm going to tell you is that for certain vertices which are neighbors to multiple polygons, if you compute that vertex normal, or if you compute the normal by interpolating the other normals around it in the neighborhood, so you can compute a normal by averaging the normals of the other triangles or polygons around it, you will actually cheat the system, the lighting system, to treat it as if it's a smooth surface. So these are just tricks we are going to be using later, but just know that this normal vector is really important in diffuse shading. And the only two vectors that are taken into account are this Wi vector, which is which is also called to light vector sometimes. It's the vector from the surface point towards the point light source, and the normal vector is the normal of the surface at that point. This W0 vector is not used this W0 is showing the outgoing radius, but this vector, we do not use it in computing the diffuse component. This diffuse component, this cosine theta, is just considering it's the dot product of wi and the normal vector, which will give you the cosine of that angle. And in specular component, yeah, the way we are going to implement it is going to be like this. You're going to reduce the light intensity with respect to the distance. You're going to take into account this distance from this point to the light source, and you're going to reduce the light's original intensity by r square, and then this is the reflectance, diffuse reflectance coefficient of that material, and then you're going to compute this cosine theta. And here, the interesting thing here is the result will be a three-dimensional vector. It's not cross product or anything. So this is a really, I mean, mathematically, I don't know, we can have such a, I mean, this KD is a vector. This I is also a vector. You're multiplying two vectors, but it's not dot product, as I said. It's, we scale this vector, intensity vector, with cosine theta, and then we individually multiply the vector's components with each other, just like dot product, but instead of adding them up, we just write them as separate dimensions of a final three-dimensional vector. Yeah, actually, this is the attenuated intensity. So, I mean, so the question is, in the assignment, we are going to use attenuated intensity. Actually, what they mean by attenuated intensity is this one. All right. I mean, if I is already attenuated, you do not attenuate it twice. So this is actually what they show here, is that this distance, this is the highlighted part on the slide, is the process of attenuation. All right. So it's the same thing as in the assignment. Okay. So it's the same. D in the assignment, the variable name is D, and the same variable D is now written here as R. Okay, they're the same thing. So this is actually describing the same thing that is in the assignment. Okay, so this is the original light intensity. This is how you attenuate it by dividing, because this attenuation will be different for every point. You cannot have a global light attenuation, a global value for a light intensity, because this d square or r square changes for every certain surface point. Therefore, you need to compute this on the fly. This light intensity is the original intensity that is given in the assignment, and this is the attenuation process that is described in the assignment. So they're basically the same thing. Yeah, in the only thing in ambient, there is no attenuation. The other component, specular, we are going to also do attenuation. So in both the specular and the diffuse shading, we need to have attenuation, because light distances. So whenever light source is needed to compute that component, we are going to apply attenuation. So this I over r square, the other component that will affect this will be the specular component, specular shading or Bilinfong shading. But ambient, a component, is not associated with a light source. The ambient component, there is no light vector in ambient. There is no light position in ambient. The ambient is independent of all light sources. So there's no way to compute distance for the ambient component. Ambient is the light that is everywhere. Okay, is this clear? For the specular exponent, we are going to have I over r square. Let's see if on the slides we have that. So, yeah, thank you. So in the diffuse shading, we will have a matte object. I mean, as you can see, this is the way we get the three-dimensional look of a sphere with the help of the light source is probably somewhere over here, if you can follow my mouse pointer. And these parts are the ones where cosine theta is negative. So we only have the ambient component, or maybe this part is totally black if there is no ambient component. But as you can see, the sphere looks really matte. It doesn't look shiny. It looks really matte. And again, the critical component of this diffuse component is, if I move my camera around the sphere, the same point on the sphere is going to have the same color. Moving the camera around the scene will not change how a specific point on the sphere is seen. Okay, it will the specific point. If you just fix a point on the sphere, and if you move your camera around, you will, for that same point, you will still see the same color. It will not change. This is not true for in real life. For example, if you have like a mirror reflection, for example, you may remember this mischief, having some kind of a mirror and trying to reflect the sunlight in your friend's face in classroom. So it means that reflected part is only reflected in a certain location. Not everybody sees that mirror point very bright. So the viewer's position is important in that specular reflected light. So that's the third part that comprises this basic illumination model, the specular component. So this in ambient, as you can see, the ambient radiance, ambient light is not going to have a position in 3D space. It's ambient, that's everywhere, so there is no attenuation here because you cannot compute any distance to ambient light source. And there's only one ambient light component we are going to use, but even if you have multiple point lights in the scene, there will be one ambient component that is going to be given to you. So with the ambient edit, as you can see, the black parts are no longer black, they become also dark gray. So it's like you boost your scene in terms of lighting. The light reaches, there is some default lighting around in the room. This is what ambient is. You don't want your ambient light to be too strong because it's just like something that is available everywhere. You just use it to make your scene less dark. And the final thing that we talked about, we are going to talk about in the basic illumination model part, is specular shading, and its goal is to simulate shiny surfaces where we have a specular patch or a shiny spot, and this shiny spot actually changes. Where that shiny spot is changes as you move your camera in the scene. So it's really viewer's position dependent. This is the different thing from diffuse part. It's view dependent. Just like when you think about specular, think about that mirror thing that you try to shine some light on your friend's eye, and where your friends actually, in this case, for example, the viewer's position is fixed, but you're trying to change the surface normal so that the reflected light from the sun is reflected towards your friend's eye. So this is how you're trying to change the reflected light to match with the viewer's position. Okay, so but in most of the cases, in most scenarios, what we have is the scene is static, the camera is moving around in the scene, that changes the specular shading. The most commonly used one is this, and one of the simplest, the Blin-Phong shading, which instead of computing the reflected ray, it computes the half vector between the light vector, to light vector from the position, and to viewer vector. So actually we can directly, I can describe it on the slide. So this is the W0 is the to view vector. Wi is the I vector, and it computes, so this half vector is computed as the half vector between Wi and W0. Okay, so this H, you compute it like this, you normalize it with its distance, so H becomes a normal vector. It becomes a unit vector with distance 1. Now, and just like we did in diffuse component, we just now this time look at they don't need to be equal. Initial, so the length of Wi and W0 initially they may be different because your camera's position with respect to this point and the light position with respect to the point, they're different. I mean, if you take the original vectors, I mean, which if this is the light position, L minus X, and E minus X, if your camera is at E, I point, E minus X, they may have different lengths. It doesn't matter. But you're saying, yeah, when you take the half vector, if there are different lengths, it's not going to be average. One of them is going to be dominating the other, right? I mean, yeah, that's. I think we can first make them unit vectors. Okay, so in order to, that's a very good point actually. If one of them is very far away, and if you just try to add them, the effect of the smaller vector is not going to be on the other. So if you really want to take the half vector, they need to have equal lengths. That's a really good point. So usually what we do is we normalize this to light vector, we normalize this view vector, and then we add them up. When they're added, two unit vectors, I mean basically you're always dividing like by 2 here, or is it like that? If you add these two vectors up, no, they may not necessarily be 2. They're not in the same direction. Okay, this is like the when you add those two vectors up, the resulting vector may have a different length if they're in different, even if they're both 2 unit vectors. But you can assume that initially Wi and W0 are normalized. They are, yeah, it may be square root 2, but yeah, it may be, if they're in the same direction, it will be just there. If you add them up, it will be 2. But if in different directions, if they are like 2 vectors that are orthogonal to each other, their distance will be square root 2. So it really changes depending on the angle in between them. So therefore, it's just good to have whatever the sum vector is. You just divide it by its length. I think that's why we cannot write here in the denominator something constant, because it's variables, right? All right, so this is the half vector, and after we normalize the half vector, it becomes unit size. We can just dot product it with n to get the cosine alpha in between them, and this is how we get. I mean, it looks very similar, right? I mean, this is the way we compute it. It's very similar. So this receive irradiance is going to be I don't know why we didn't have this. So here the receive irradiance here actually the light, you're having the same light intensity that we receive here. It's going to be same I over R square here. Okay, so yeah, from this Wi is from this light source, whatever we are receiving, this is the same thing. If you're using light attenuation, it will be same as I over R square, just as in diffuse. And this is the specular reflectance coefficient, and this is the cosine alpha. It's very similar to the diffuse component. Okay, now as the angle h moves away from the normal vector, you're going to have reduced specular exponent, specular component. Now I come to specular exponent, which is this p. Sometimes it's called the Phong exponent. In order to have an additional property, to have this specular component not decrease as if it's in diffuse component, if you want for very shiny surfaces, I mean, if it was, let me show you this one, for example. If you have a point light source, look at the one sphere on the right. If you have a point light source, if this was as shiny, as super shiny as a mirror, would you be able to see a large area that is bright like this? The answer is no. You will just see a point. A single point will be, because you have a point light source, only one of the points will come perfectly to your eye. Okay, I mean, if you multiply it with cosine alpha, of course, you're going to be actually seeing a larger bright spot. But what I'm saying is that forget about this cosine theta thing. Just think about the thing that, I mean, if it was really like a mirror surface, and if we have a point light here, in order to only in one of these points, the reflected ray W0 will be equal to W0. I mean, the light source will come to this one at only a single point. So this tells you that, I mean, the way we multiply it with cosine alpha is that we actually make this mirror less like a mirror, saying that, okay, even if it's a point light source, if the viewer is here, it can receive, we actually make it a little bit diffuse, because we are saying basically by multiplying it with cosine alpha, we are basically saying that even if the camera was over here, it will still be able to see this reflected light, because it's not a perfect mirror. So it's like it also diffuses in some kind of a cone. And in order to play with this property, whether being at the one extreme, you may be at the one extreme, you will be a perfect mirror, in which case the point light source will be seen bright in only at only one point on the sphere. At the other extreme, it becomes also like a diffuse light source, in which the whole reflection from the point is diffused over all of the sphere again, so it doesn't make it any specular. So therefore, in order to make things in between, we have this Phong exponent. For example, if you give this Phong exponent a very large number, if you give, for example, 1 million, imagine, given 1 million here. So even if this cosine alpha becomes 0.999, okay, very close to 0 degrees. If cosine alpha is 0.999, it means the two vectors are very close to each other. If you take the 1 millionth power of 0.999, it will be almost 0. Okay, so any number less than 1, if you take successive powers of it, you're making it closer to 0. Which means that with a high Phong exponent, only if cosine alpha is 1, you will be able to see bright spot. Otherwise, everything is going to drop back to 0 with a very large Phong exponent, if it's 1 million. But if it's 10 or 100, this is what we see actually. The specular exponent will allow you to have this specular spot or shiny spot in a certain smaller area. The larger the Phong exponent, yeah, look at this. Yeah, 1 million is actually, I exaggerated a little bit. So thanks, Bugra, for this computation. It's 10 to the minus 435. It's practically 0 for... and even if you're using double precision, it's practically 0. Therefore, no amount of light is received if you have a really large Phong exponent. So some values of Phong exponents are 10, 20, 100, maybe at most if you want to have a... when you increase this Phong exponent, this shiny spot that you see is going to get smaller and smaller and smaller. Large Phong exponent, if the Phong exponent is small, that power is small, this shiny spot is going to disperse. It's going to occupy a larger area on the sphere, like this. This is a very low specular exponent. As you can see, it becomes like a diffuse, almost. Maybe it's like when you give 1 to that p, if you give 1, can you give... I think it has to be an integer. If you give like real values, like taking the square root of, you don't want to do that. You don't want to take square root of cosine alpha. It's that Phong exponent usually is some integer power. All right. The smallest it can be is 1, and when it becomes 1, it becomes like the diffuse, it becomes like a diffuse sphere, no specular exponent. And if you look at this, maybe it's like 5 here, maybe it's like 10 here. It becomes the exponent, the shiny spot becomes smaller and brighter. Yeah, so for lifelike rendering, the exponents should be kept at a high level. Depending on the material. If you want to visualize billiard balls, which are shiny, you may use different Phong exponents. So really, the Phong exponent, whatever value it is based on what kind of a material you want to model. If you want to model a matte object, you keep it at 1. If you want to model shiny material like this for your sphere, you raise it. So it really depends on what kind of an effect you want to have on your material. This is also lifelike. This is really what is lifelike? It depends really on what you want to model. Okay, so it depends on whatever you want to model. Okay, if you want to model a plastic ball you don't want it to be too shiny. An old plastic ball, for example, you don't want its specular spot to be too shiny like this. And when we put all this together, it becomes diffuse plus ambient plus specular. They're all additive, all right? So everything is multiplied in vectors. And when we have multiple light sources, we may have multiple light sources in the scene. What we do is the ambient component is added only once. And for all of the light sources, so from 1 to L is the number of light sources, we compute the diffuse and specular component for each of them separately, and we add everything up. So all of the light computation we perform is additive for that spot. Okay, so this will give you, for example, there are 2 light sources on the sphere, which gives 2 different specular shiny points, as you can see, and they're all added up. You need to be very careful about this adding up, because if you have a lot of light sources, when everything adds up, you may end up all the points becoming 255, 255, 255. They may saturate and they may all become white. So playing with these parameters is really not easy. You need to consider putting lights in different sources in different places. So when I tried to first designing a scene is very difficult. For example, I put light sources in different places, but some place remains dark all the time. I want to make it lighter. I move this, another place becomes dark. So really putting all these things together, I think you may have to have some kind another education, like directing movies or filmography. So it's something else. I mean, where to put the lights, which part is going to stay dark, which part is, what kind of material properties you should set. So designing these scenes is really something else that needs another whole semester or whole year course on it. So the ray tracing algorithm so far with the basic elimination model is this. The first part is the same. Now pixel color, instead of adding the pixel color directly from the material, you just compute the pixel color with respect to the things that we have, with respect to this right hand side. Ambient, diffuse, and specular, they're all added up to compute this final color of that. And at this point, we can see things like this. So this is how, at this point, we can see spheres or other triangles like this. It puts some realism into the scene, but still we need to do 2 more things. And in the final 12 minutes, I will talk about them. So shadows, they give a lot of realism to the scene. In OpenGL, for example, shadows are not provided by default because in the forward rendering pipeline, in the other algorithm, not ray tracing, in the other algorithm that we're going to see in the second half of the course, generating shadows is not easy because each object's color is computed independently from the others. So, and having shadows requires you to consider interactions between objects. Shadows are nothing but objects occluding other objects with respect to light sources. For example, for this X point to be in shadow, there has to be some opaque object between this light source and this point. So this is what we will simply do. The way we are going to implement it is to have a shadow, something as binary. Actually, there is also the term soft shadows, in which you can actually make this shadow not binary, but fractional, something fractional, by looking at this neighborhood point. And the idea is really easy. Imagine we have like a 5x5 grid around this point with some neighborhood points. I look at its 25 neighbors and ask each of them the same question. Are you in shadow? Are you in shadow? Each of those 25 points give me Boolean answers. I'm in shadow, I'm not in shadow, I'm in shadow, I'm not in shadow. And whether this point is in shadow or not becomes a fraction of the neighbors that are in shadow. Okay, so you can actually, this way, for the boundaries of the objects, you can actually create soft shadows, which are actually due to lights that are not being point lights. So aerial modeling aerial lights with some that occupy a rectangle, for example, is not easy. It's very difficult. Some global illumination models like Radiosity consider that, but for our introductory computer graphics course, we're just going to consider point light sources. And if you have point light sources, your shadows will be really not smooth. The edges will be edges of the objects will be just cut out from black to white. I mean, whatever color they are. Okay, by the way, they're not going to be completely black. If the shadow is going to be computed again per light, which means that being in shadow does not affect ambient component. The ambient component is always added to this point X. We will always add ambient component because ambient is everywhere. Whether there's an object or here or not, it doesn't affect the ambient component. But the diffuse component and the specular component coming from this light source will be affected if there's an object in between. And the way we implement it is very simple. We already have an procedure, a function, which intersects rays with objects, right? In order to determine this point, we have intersected our ray from the eye through the pixel center with the objects in the scene. Now what we do is we generate a ray from this point to the light source. We also have that ray, which is a to light ray. You can keep it in unnormalized form to get the direction. So the ray equation becomes x plus to light vector t. Okay, so the parametric ray equation, you can form it easily. And now you intersect this parametric ray with all of the objects in your scene again, once more, another set of lots of intersections in the scene. If there happens to be an object which intersects this ray with between t is equal to 0 and t is equal to 1, it will be t is equal to 1 here if this ray is like this, unnormalized. Okay, if you normalize it, then you need to look at the distance between. If the distance between, actually you compute that, right? The r or d. I mean, in the slides it was r, in the assignment it was d. You compute the distance of this light source to this point x. If this wi is a normalized vector, then when will we have shadow? When we will have shadow, I will write in the chat box, when t is between 0 and d, if d is the distance between x and the light source, and wi is a unit vector. If these are the case, if you normalize wi, there will be shadow when the intersection, there happens to be an intersection in which t is between 0 and d, where d is the distance from the point to the light source. Okay, so this is, we determine the shadow like this, and it will be something binary. If the the point is in shadow due to this light source, what do? The only thing we do is we do not add, remember this summation. If there's a shadow for one of the light sources, one of the eyes, then we add 0 for that light source. That light source will not have any diffuse or specular component added to the overall lighting. So therefore we need to compute the shadow rays L times. If we have L light sources, for each of those L light sources, we compute the shadow ray. We determine whether there's an object that intersects with this ray or not. So if you have, for example, 4 different light sources in the scene, you generate 4 rays, and those 4 rays are intersected with all of the objects in the scene. And for each of those light sources, we determine whether there's shadow or not. And yeah, and this is the, as I said, this is the shadow ray. And if there's intersection before the light source, then the point is in shadow. Sometimes when you're doing the intersection, when you're checking whether this, I wrote here in the chat box t is between 0 and d, but when t is equal to 0, if there's an object very close to that, that may actually cause a shadow, but you should not intersect the ray with the object itself, with the object's triangle, because there will be an intersection. The ray will intersect the object itself at t is equal to 0, but because of floating point imprecision, the intersection, the t, for example, may be considered sometimes 0.0001, and it will be for having a shadow. Therefore, we have this intersection value. At least either you do not intersect the, sometimes you may flag the triangle itself so that the ray is not intersected with the object itself, or you may use some epsilon value to avoid self shadows. Okay, an object cannot cast a shadow on itself. All right, and now this is how the shadow was implemented, and the final image looks like this. It looks very nice with the specular. There are 3 light sources here. The normalized Wi is not multiplied with epsilon actually. I mean, actually they multiplies with epsilon, but I would not actually implement it like it. Okay, so the epsilon here is like moving. Its effect is like moving our point slightly epsilon units. So we start our, it's like starting our intersection, even if t is equal to 0. I mean, actually, it's like you may treat it like you're moving the vector a little bit up, but I would not implement it like this way. Actually, what I would do is, instead of implementing multiplying with epsilon like this, okay, I will leave it as original, like this. It's, oops, I cannot delete these. Okay. All right, so I will keep it like the x plus twi. I will keep it like this, and I will check the final t value. Instead of t greater than 0, I would check whether t is greater than the epsilon. Okay, you can also implement it like this. Both are possible. Okay, and the final, so image looks so far much better, and the final thing that we're going to add are going to be reflections, and this is where ray tracing becomes recursive, and we have something, the term, the light coming from the light source could actually be due to reflection from another surface. So the light that is coming, there are, for example, there are point lights here. Okay, what if light rays that are coming off other surfaces of objects are also like point light sources? Okay, so here we will also try to determine, okay, if there's some light bouncing off, there's something that is bouncing off here, and I also want to see that. This is like a specular reflection, but not due to this light source, but due to some reflection of that light from another object. So can we also take into account by tracing the reflection path of our light rays in the scene? And that becomes that allows us to actually see, for example, at this point, your lights, even if your lights are all white, and if you have a blue sphere here, if that blue sphere is very reflective, and if this is some kind of a red sphere, you will see some reddish spot due to red light reflecting off here and coming bouncing off the surface. Okay, so there will be some reddish light coming off this other sphere in the scene. And the way we implement is like this. It's recursive because just consider this reflected ray. Okay, this is our primary ray. Look at this ray, which reflects off with respect to the normal vector. At this point, if you just focus on this reflected, let me get, can I get a different, oh, I think I have to be in full screen mode. Yeah, pointer options, pen. Now, look at this reflected ray. I'm going to mark it as red. Now, what we do is we consider as if there is an eye point here, okay, as if this is the view vector, and we ask ourselves, what color is this ray? So in other words, if there was a tiny image tiny image plane that was here, and this was a single pixel that we shot through some ray, and this view vector is the ray that we shot through this tiny pixel at this point. What color would we see due to this new viewing ray? And this becomes the exact same problem as we try to solve here, right? I mean, this is the actual eye, this is the actual image. We are shooting pixels through the image, and we are trying to say, what color is this ray? And we compute it by this surface. Now I do the same thing. I ask the same question this time for this reflected ray, saying that what color, if there was an image plane here, what color of pixel that I would see if it was this ray, if there was an eye point that is here, if the eye was looking in this direction, what color would it be? I asked the same question recursively this time for this ray, and I incorporate the reflected color coming from here by multiplying it with some weight, because if I directly apply this color to this one, it becomes this object. If it's like a mirror object, if it doesn't have a color on its own, it will see whatever this view reflected ray see. It will be like an exact mirror. It will be like a mirror sphere. But usually objects are not mirror-like, but they have some reflection, and this is how it happens. Okay, so this is the recursive part. Now the final part is we compute this reflected ray, and this reflected ray becomes like our new viewing ray, and we compute everything, the color for that reflected ray this time. This becomes and we continue doing this for a certain number of steps. You may ask the same thing. When we are computing this reflected ray, from that point, it will also reflect to a new location. Okay, if you look at this, from here, it's also reflecting. What if there's an object here? What color of this point? The color on this point will be affected by the object color that is if there's an object around here. So we continue this process only for a number of steps, like 2, 3 at most. Yeah, it's not binary. It can reflect 50%. That's exactly what I wanted to say actually. If it's like mirror, it would reflect 100%, and whatever reflected color we compute, we are just going to place it in the actual image plane. So if the reflection can sometimes be 100% of the color can be due to the reflection, or sometimes it's 50% for certain objects which do not reflect anything. The other objects' color are not affected on them. It may be 0%. It's not binary. So we are going to actually implement it by multiplying it with some. For example, if you look at this, the only surface that is reflective here is this triangle or the tabletop these two spheres are on, because as you can see, this doesn't have a specular component. This is just diffuse. This has lots of specular, and this tabletop itself is very reflective, and part of it is gray. So we see grayish color, but we see some bluish color here, which is the reflection of this sphere on it. So 50% of this point, for example, if you look at this point on the table, your view ray is going through there and bouncing off and hitting the blue ball at this point. And we get this blue color that is hitting here, and we just multiply it with some constant, like 50%. Again, it's the material property. So in the assignment, so I'm going to finish off here and finalize ray tracing on Thursday. But if you look at this, the material properties, there is also this mirror reflectance property. So this mirror reflectance property is exactly that thing that you're asking. It's whether it tells us 50%, 60%, 30%. That's this mirror reflectance property, which will be different from each material to material. For some materials, it may be 0. For some of them, it may be 50, 60, 70. If it's a perfect mirror, it may be 100%, and which means that the diffuse, ambient, and specular, you will just ignore them, and you will just treat it as if it's a pure mirror. Okay, so that's it for today. I'm going to finish off this reflection part, I'm going to recap on Thursday and finish the shading part of ray tracing. Actually, it's already finished. I mean, the details that I'm going to talk about are this mirror reflectance property, how you can incorporate it into your code as some kind of how are we going to multiply it when we're adding them together. This is the part we multiply mirror reflectance coefficient with this value. So after that, we will finish the basic ray tracing algorithm, and we will then talk about texture mapping. Look at this tabletop. It's like a nice wood texture, and this nice wood texture in the next part of the slide set, we will talk about texture mapping in ray tracing. Okay, so these are some nice ray traced images. You can also have transparency in ray tracing, or even refraction. Look at this, the light, as it moves through the transparent object, the light is refracted, meaning that different wavelengths or different color lights are reflected in different directions. So that this gives really nice looking effects. Okay, we're not going to talk about these in this course. These are really advanced ray traced images. Okay, so these are really some nice examples of ray tracing, but there are other effects. Now I'm going to stop here, and we're going to talk Thursday about texture mapping, and I'm going to finish off ray tracing shading. All right, thank you everyone for attending the lecture. See you on Thursday. Take care. I'm going to stop recording.